We're going to be talking about multiple linear regression, which is an extension of simple linear regression and a topic you have seen earlier. Okay, so let's get started with a particular study. And the question being asked is, why do some mammals have large brains for their size? Okay. And this question relates to the context of evolutionary biologists who are interested in the characteristics that enable a species to withstand selective mechanisms of evolution. And an interesting variable is the brain size. Okay. Why is that useful for survival, for instance, might be one main question. Because the brain, it occupies a large space and it requires more energy the bigger your brain is. So the more the thought is, the bigger your brain is, the harder it might be to survive. And there are certain drawbacks to brain size. Brain sizes are associated with fewer offspring and longer pregnancies. So, if you have fewer children and fewer pregnancies, why would it be an advantage as a survival mechanism or to have a larger brain? Okay, these are the sources, these two right here, and let's have a look at the data. So these are the average values of brain weight, body weight, gestation or length of pregnancy, and litter size for 96 species of mammals. Okay, so for example, we have a badger. They have a smaller brain size of 53. I believe that the unit of measurement is missing here, but if you go to the original source on the previous slide, it will say specifically it has want to say 6 kilograms, but that's its unit of measurement, and its gestation length is 60 months, and it has a litter size of 60 days, I'm sorry, a litter size of 2.2, okay, on average. Okay, so in our previous material, we've seen simple linear regression, and it would be useful to answer some specific questions. So here's a simple linear regression, which we can perform, and it's the brain size versus body weight. Okay, and we get these calculations. So here's the coefficient, there's an intercept, there's a slope for body weight, and it says for every additional unit of body weight, brain size increases by 1.32 units, and the baseline is 74.93 of brain size. Okay, of course this intercept doesn't quite make sense because we don't know any species with 0 body weight. Okay. I want to talk in particular about these p-values. So the intercept being 0.007 and less than 2 times 10 to the negative 16th. What does that mean? So these two are p-values. They relate to a hypothesis test. And we're going to come back and talk about that a little bit, but I'll give it away a little bit. This p-value right here, it's a test of hypothesis that body weight is important for regression, that it affects brain size. And the alternative hypothesis would be that it does not. So the null hypothesis is that I switched the two. The null hypothesis is that body weight does not affect brain size. Okay, the alternative is that it does. Okay, and by the way, if body weight doesn't affect brain size, we'd expect an estimate of 0. This is not 0, so it seems reasonable. Our p-value is in agreement that body weight affects brain size. But the p-value and the estimate are two different things, so do not confuse those two. So this p-value says that it's less than 1%. In fact, it's 2 times 10 to the negative 16th. Okay? So very statistically significant, less than 1%. And it's important for the regression equation. Likewise, it says that this intercept is important for the regression equation. Okay, a few more things on linear regression is that we can predict brain sizes for other animals. For example, the axis deer has a body weight of 89. And to predict the brain size, we just plug it into the equation. We take our intercept 74.92, we take 1.32, and we multiply it by 89. That's our predicted value. But this is off from the actual of 219. And we can calculate what's called a residual. That's the difference. Okay. Another important measure that you'll see is SSE. And that is the sum of the squares of the residuals. So that is, you would take this residual and you'd square it, but you do it for every single observation. You square the residual of every single observation and you'd add it up. That's what this formula says. I'm sure it's a little bit confusing. So if this equation is confusing, just think that the sum of the squares of the errors is you take all your residuals, you square them, and you add them. One reason we're interested in this is because the smaller the value of SSE is a better indication that the regression line fits the data. After all, if SSE was 0, that would indicate that we perfectly estimate every single value. Okay. Now, perfection typically isn't possible, but the closer you are, the better. So the closer you are to 0, the smaller your sum of the squares of the error is, the better. Okay. Okay. So this slide relates to p-values. Okay. So the coefficients and the slopes are calculated for the data, and that's different from a p-value. However, if we were to collect another set of data, we would get slightly different estimates. Okay? And that tells us that the slopes and estimates are random. Okay? Is it possible that due to this random error, the estimates could be 0? That's what the question that we're trying to answer is. Okay? So a test of hypotheses of m equals 0 versus the alternative that m is not 0. That's what those p-values are trying to answer. Okay. If the null hypothesis is true, that means that x does not play a role in affecting y. Okay. And the null hypothesis indicates that y does not depend on x. You just have a simple prediction, y equals a constant. Okay. The alternative hypothesis, indicates that the variable x is important for regression and its impact on y is given by its estimated coefficient. And it should be included in the regression of y. Okay. Now let's go back. We go back to this slide. We see that the coefficient of body is 1.32, but more also very important is its p-value. It's 2 times 10 to the negative 16th. That means it's statistically significant at more than the 1% level of significance, or smaller than that. Okay, so it's very statistically significant. Okay, and it says it's not possible, or it's very unlikely, that this estimate could be 0. Okay, it's very, very unlikely. Okay. So it is important for predicting brain size. That is the body weight. Okay. Now going back to this, notice that it says, hey, there's this t. The p-value depends on this t statistic. Well, this t statistic is calculated as follows. This is the t statistic. You take your estimate, m, you divide it by the square root of the sum of the squares of your errors divided by 2 less than your observation size, and you take s, the standard deviation of just x, and you multiply it by 1 fewer than your observations. This is your t statistic. Okay, your t statistic has n minus 2 degrees of freedom. N is your sample size, s sub x is the sample standard deviation of x, and m is your coefficient of the variable x. Okay, and that was provided in the regression output. That is what m is. Okay, so going back here, I've highlighted, here's your t values. These two, 16 for body, 2.71 for the intercept. These are the p-values, okay? And notice if the null hypothesis is true, we expect that SSE will be large relative to the estimated slope, okay? So SSE is important for trying to determine how good your model is, whether you expect one null hypothesis to be true or false. But the main emphasis here, the main thing is on this red highlight, the p-values, okay? It tells us that the variable of body weight is important for the regression equation of brain size, okay? And based on the output, we reject the hypothesis that the slope of body weight is 0 at the 0.1% level of significance. But we could even change this 0.1% to be smaller, since it's 2 times 10 to the negative 16th, much less than 0.1%. Okay, so this is our conclusion. I've highlighted it here. That's the emphasis of these slides so far. Okay, let's run another regression equation. Notice our data had another variable, which is gestation length, how long it takes for a pregnancy to occur. Okay. And our question is, does the length of pregnancy, does that affect brain size? So different questions for different regression equations. Notice that. Okay. And we come up with an estimated value, but also, very important, is we calculate a p-value. That's 2 to the negative 16th also. So gestation is very statistically significant for determining the brain size. Okay. On this information, we can reject the hypothesis gestation is 0, and we conclude that gestation is important for predicting brain size. We can also state our regression equation for brain size. It's right here, and that comes from our estimates here and here. Okay. So be prepared to state the equation, and also to make conclusions about p-values. Okay. Now, one question that's being asked here implicitly is if gestation is important for regression, but I also used an equation that has body weight. Well, how do we incorporate that information to make an equation for predicting brain size? And the answer is multiple linear regression. So this equation right here is an equation that of multiple linear regression. And here there are k variables. Here we're just going to have 2. Okay. We can, just like before, we can test hypotheses that individual coefficients in multiple linear regression are 0, and we can calculate predictive values, residuals, and assess the regression equations. Okay. Another thing that's very common in multiple linear regression is that we can use what's called a categorical variable or a dummy variable if you have a category. Okay, and a typical category could be like city, state, gender, sex. Okay, and we'll deal with that as well. But let's continue. Okay, so let's deal with a two variable, k equals 2, in our multiple linear regression. Okay, and what we're going to do is we're going to use both gestation and body weight to predict brain size. And when we do that, we get slightly different estimates. So notice the intercept has changed. Our estimate has changed a bit, and for both these two variables of gestation and body weight. But notice they're highly statistically significant. Gestation is statistically significant at 8 times 10 to the negative 7th. And body weight is statistically significant as 2 times 10 to the negative 16th. So both these variables should be included in the regression equation for brain size. And it provides us our RSE, residual standard error. It provides us with the multiple r squared and what's something that's called the adjusted r squared. Okay. And we'll talk about adjusted r squared in a minute. But I just want to state, the important part is the p-value. That's what's new for us. We should also be able to form the regression equation. But based on the p-value, we conclude that both the variables of gestation and body weight are important for predicting brain size, which is measured in grams. And we conclude for every additional day of gestation that brain size increases by 1.44 grams, holding all other variables constant. And for every additional kilogram of weight, the brain size increases by 1.03 grams, holding all other variables constant. Okay. Now let's talk briefly about this adjusted r squared. The adjusted r squared is an estimate of the proportion of variability that explains the data. And r squared is another variable that does this. However, r squared estimates 80% of the data is explained by this equation, and that's really good. Adjusted r squared is a little bit more conservative, so adjusted r squared is slightly less, so this, these two values are very, very close, but adjusted r squared is always going to be slightly smaller. Okay, and the two variables are always going to be pretty similar, but adjusted r squared is always going to be slightly less or more conservative estimate. Okay. One reason why we might use adjusted r squared is because it is more conservative. Okay. When we use just r squared, it can overstate the amount of variation that the model explains. So the adjusted one is more conservative and it hence always less. Okay. We think that that is the better and safer measure to go with generally. Okay, so just going back to the equation from the output, we can form the equation just by using the estimates. And our brain size is predicted by minus 112.19 plus 1.44 times gestation plus 1.03 times body weight. And that comes from the regression equation, or the output. And any time we include an extra variable, we have to re-estimate the regression equation, because notice it changes slightly. Now, if I want to find the predicted value for an axis deer with body weight 89 and gestation period of 218, then I just plug that into the equation. So I put the 218 here, I put the 89 here, I perform the multiplications and the additions, and I get 293.4 grams. And notice that 293.4 is not the same as what we observed. Okay, so we observed 219, we predicted 293, so we can form the residual, which will be minus 74.4. Okay. Now, multiple linear regression has assumptions. Let's briefly go over that. Okay. The assumptions are that the residuals are normally distributed. Oftentimes you'll see a textbook just state that the data is normally distributed, but the two are synonymous. If you do the data versus the residuals, some textbooks say residuals, some say data. I'm okay with either one, and generally by data they mean the y variable, which would be brain weight. Okay. There is constant variance for all input variables. The observed data is independent, so one observation doesn't affect the other. That seems reasonable here. And, we stated our belief on why the data is independent. That's all that's required in this course, and that's all that's really possible. Okay. For the other two assumptions, we'll assess them with some graphs. Okay. So here's a graph of the histogram of the residuals. The histogram indicates the assumption of normality. Hey, it doesn't look perfectly bell-shaped with a peak in the middle and a symmetric curve to it, according to this histogram. Okay, it looks kind of skewed. So the assumption of normality, we would say, is weakly violated. It does have a peak. It has some resemblance of symmetry. And now let's look at the assumption of constant variance. That is, as the any of the x variables change, we'd like to see the residuals line up all about 0 at this dashed line. Now, I want to add that this red line here is imposed by the statistical software. This red line can be deceiving, and you should mainly look at the dots. Okay. If we have constant variance, we expect the error to remain relatively constant at 0, but it appears that this is not the case. Okay. That is, as the fitted values increase, the error is slightly underestimating the values in general, except for this one point on the far upper right. Okay. But in statistics is about the general trend, not one point. And this cluster of points below the x-axis in the middle to beginning kind of indicates, hey, it's underestimating what values we should have. Okay. And so we would say, hey, it looks like this may not have constant variance. Okay. It's not, when you're expressing assessing the assumptions, I'd like you to know that it's a spectrum. It's not true or false strictly, but there's sort of an in-between. It looks like there are some violations. It looks like there's a lot of violations. And to go into a little bit more of indicating where it is on this spectrum and why. Just very briefly why. I don't need paragraphs. Okay. Okay, now one other thing I want to talk about is dummy variables. So an example of a dummy variable could be sex, in which there's just male and female. So here you can code a variable in a multiple linear regression model to take a value of 0, 1, male or female. Okay. So if you saw an input of male, you might put a 1, and if you saw an input of 0, if you saw an input of female, you might put a 0. Okay. However, it doesn't require it just to be one of two variables. You can do dummy variables that are more complicated, such as cities, etc. Okay. But for today, I'm just focusing on the two variable case, male or female. Okay. And we can perform a regression now when we have a male or female input, and we're going to consider that example. Okay. In this example, the variable sex takes on a value 1 if male or 0 if female, and we're going to use this variable to model starting salaries, okay, at the time the data was collected. Okay. So this data was taken at an actual bank, okay, in which there are 32 males and 61 females. And here's a brief little preview of the data. So we're going to model this base salary, starting salary, and we have variables of sex, seniority, age, education, experience. Now, I will say, if starting salary is determined by this variable sex, and we have ways of determining if it is likely determined by sex, which is via the p-value. So remember, the p-value would tell us if sex male is important and should be included for predicting starting salaries, base salary, or not. Okay. But if that variable is used in predicting starting salary, then the bank might be guilty of sex discrimination, which is illegal. Okay. Now, if age was important for determining starting salary, the bank might be guilty of age discrimination as well. However, age discrimination is not a great one to use, and not the question we're being asked here, because age is confounded by experience. Okay. So instead of using age, we could use experience if we want, because that's the actual thing that I hope, someone's age wouldn't affect their starting salaries, and there could be other variables that explain it, such as experience. Okay. It could be that education, which is related to age, affects starting salary. So there's all sorts of information that the hard data does not fully answer, and it's worth considering. Okay, so the idea is, can we use any other variables other than sex to try and explain starting salary? Okay, so perhaps it's just random chance. Someone might say that males are paid more than females. Well, that can be assessed through a p-value or a t-test. However, it's possible that the males just happen to have a higher level of education or experience because of random chance. And we could see if that is the cause of gender discrimination, of a pay disparity, not gender discrimination, but a pay disparity in that case. So let's explore it. Okay, so perhaps there is a reason that there could be a difference. Okay, and let's consider a model without sex. Okay, so I'm going to include all the other variables to see if how effective they are for predicting starting salary. And we can see, hey, seniority is very statistically significant for starting salary. Age is not. Okay. Education is very important for predicting starting salary, and so is experience. Okay. And this provides an R squared of about 28% on the conservative side. Okay, so it explains about 28% of the data, this model. Okay, and this does not include sex. Now, the key in this analysis is considering two models, the model without sex and the model with. Now, I'm going to compare the model with sex and see what happens. But first, let's just state a few things. After all, we have this output so we can form the equation. So this just sums up what I just stated. Okay, we would state our model and see this. Okay, and that gives us 28% of the data, or explains that amount of the data. Now let's compare when we add the variable sex. Okay, notice our estimates all change. Okay, so here it is. Here's our equation. But notice the variable of sex male is statistically significant at 5 times 10 to the minus 8th p-value. That means despite the fact that we used age, seniority, education, experience, it still does not explain the data as well as if we included the variable sex male, because it has a p-value of 5 times 10 to the minus 8th. Okay, and it also explains 48% of the data based on the adjusted R squared. That's a bump of about 20%. So just by including one more variable, which has a p-value that says that you should include it for predicting starting salary, and it explains 20% more of the variation in the data, it seems like the variable sex needs to be used for determining starting salary. Okay, now let's just write down our formula. Our overall model, we just take it from this estimates right here. Okay, so hopefully we write down everything that we had before. And, you know, I kind of rounded in some places because it's hard to fit in the screen, but this would be our regression equation. Now here, sex male is a dummy variable. It takes a value of 1 if the individual is male and 0 if female. So there's two equations. I just plug in 1 for a male starting salary. It has all the same variables, but it has an additional $767 for the date range of this data, which was the 60s and 70s. Okay, the female starting salary gets a 0 for that variable sex male, so it just doesn't have that last estimate of $767. That means that the coefficient sex male, that is the pay disparity. That's by how much these two wages for these two populations differ. That's the estimate. When we use, and notice that that is when we use all these variables, seniority, age, education, and experience, to try and explain starting salary. We'd have different conclusions for different variables, and it's also possible there could be other data to consider. Okay, so just to the conclusion, based on the p-value, which is one of the main points, p-values are really essential in statistics. The p-value tests that the variable sex male is important for regression, and we can reject the hypothesis that the coefficient is 0, which means that the variable sex male is important for starting salary, for determining it. Okay. Another key takeaway is the R squared value. The adjusted R squared is what I'm using here. And it says that the proportion of data that this model explains is about 47.3. And let me just, excuse me, it should be 48%. So this is 48%, my apologies. And versus the 28, I believe. Yep, 28%, so that's a typo. My apologies here. 28% from the previous model that excluded just the single variable of sex male. Okay, and what this conclusion does is it's accounting for these variables. So if an individual has the same level of seniority, age, education, and experience, the starting salary of the individual of this bank will differ by $767. And that's also what we estimate by the pay gap. This estimate is statistically significant. Okay, so here you can see a few applications of p-values and multiple regression. I hope that you've enjoyed this lecture. Thank you.